All right, welcome back, AP. We have 10.4. We have two additional gas laws we're going to learn in this video. One is called the combined gas law, and the other one is the ideal gas law. Let's start with the combined gas law. All gas laws that you've learned so far in video 10.3, Boyle's, Charles, Guy-Lussac, and Avogadro's, well, pretty much what the name says is we combine all of them together. So when you work your math, it's best to start with the combined gas law, and then all you have to do is write down the combined gas law and cross off any variables that remain constant. And I'll show you what I mean when we get to our first example. What's constant? Well, anything can stay constant. Anything can be constant. So with the combined gas law, you have what's called P1V1 over N1 N1T1, and then on the other side, P2V2 over N2T2. Well, I don't like to deal with fractions too much, so I like to write it this way. So basically, if you cross multiply, then you get this. P1V1 T2N2 equals P2V2 T1 N1. As always, the ones are the initial conditions, and the twos are your finals. For pressure, you can use any units as long as they're the same. For volume, same thing. We typically like to use liters, but you can use mils. Temperature, you have no choice. It's got to be in Kelvin. So remember, you take your Celsius and you add 273. And moles is moles, okay? Cannot have grams or molecules, okay? So let's try an example. With the combined gas law, it's very important to label everything that you see, the ones and the twos. So we have diborane gas, which is B2H6, and it has a pressure. So automatically I know this is my P1. And it has a temperature, which I'm going to have to convert that temperature, and a volume. So I actually know all my initial values. If the conditions change to a temperature, so now I got a new temperature, so temperature went up, and the pressure looks like it went up too. So there's my P2. What will the volume be? Well, I'm solving for this new volume. Okay, so first thing is, let's tackle those temperatures. Let's get those T1s. So negative 15.1 degrees Celsius. So we have to make sure we first show AP, our equation. So 273.15. And with our calculator, now that's a negative 15.1. So this answer won't be greater than 273. So I'm going to get 258, but I do need one after the decimal, so 0.1 and then Kelvin. For T2, it went up to 36.8. So 36.8 plus 273.15, and I'm going to get 309. I only need one after the decimal, but it's 9.5. So I actually need to round that up to 10.0 Kelvin. So going back to the top, where when you work the math, start with the combined gas law. And this is the combined gas law because pressure change, volume change, temperature change. Write down the combined gas law and cross out the variable that didn't change. Well, if you notice in the story, so P1V1 T2 N2 and P2V2 T1 N1, who did they never mention? Well, they never mentioned moles. So moles must have stayed constant. So if moles didn't change, then cross out the moles variable. So I need to solve for that volume right there because I'm solving for the new volume. So it's cross multiply, but I have to get P2 and T1 to the other side. Okay? So then I have my equation, V2 equals P1 V1 T2 over P2 T1. So you already have your equation here. You don't have to write it again, but be very careful with the ones and the twos. So my initial pressure was 3.45 torr, and my volume was 3.48. My T2 was right here, this 38 degrees, which is 310.0. And then my P2, pressure 2, was 468 torr. And then my T1, my initial temperature, was 258. Okay, so pressure is going to cancel. Kelvin will cancel. Now, what's tricky about the combined gas law, it's not the math, it's plugging it in the calculator. So I'm going to do this in a different colors, but you need to practice your calculator of how you plug it in. We're obviously going to multiply these three numbers on top. Hit the equal sign, but keep the number in the calculator. So whatever your number says, don't worry about rounding or sig figs. And then you're going to hit the divide button because 468 is in the denominator. Hit the equal sign again, and then hit divide, and then 258. Hit that equal sign. Now that you have that final answer, that's when we care about sig figs and rounding. So it looks like I'm going to need 3 sig figs. So plug it in with me together. 3.45 times 3.48 times 310. And then divide 468. Hit equals, and divide 258. Every calculator is different. For those of you that have like maybe graphing calculators or certain scientific calculators, you can use parentheses. The problem is not every calculator does it the same way. So you have to find the way that works for your calculator. So 3 sig figs, I get 0.0308. And because I want volume, I have liters. And then it's this gas B2H6. Okay? So anything can stay constant in the combined gas law. But as I said, the tricky part of it all is just plugging it in the calculator. So let's do a good review before we even tackle the ideal gas law. So first law that we learned in the last video was Boyle's law. Boyle's law has an inverse relationship. I didn't think it was going to let me write too much in there. So an inverse relationship, which means if pressure goes up, well, it just doesn't like me writing there. So I'll write it over here. Maybe I can write it here. Pressure goes up. There you go. Volume goes down. Okay. So if I push on a balloon, I'm going to decrease the volume because I'm bringing the gas molecules, as you see right there, they're closer together. Okay. These are more far apart. And what would be my formula? Well, because it's an indirect relationship, it is the only equation that has the 1's and the 2's on the same sides. What has to be constant? So for it to be constant, you have to have temperature and moles to be constant. Okay, so inverse relationship. Charles's law looked at volume and temperature, and as you see the straight line, direct relationship. So if volume goes up, temperature goes up. Okay, so if we crank up the temperature in that balloon, oops, not quite sure what happened there. If we crank up the temperature in that balloon, you're going to make the molecules go faster, gain some kinetic energy, which we talked about, and that will make the balloon bigger. So now we have V1T2 is V2T1, and what has to stay constant? Well, has to stay constant is pressure in moles. Okay. I'm going to go to Gay-Lussac's down here, and I apologize, I should say Gay-Lussac, not Gay-Lussac. Gay-Lussac's pressure and temperature, same thing. If pressure goes up, temperature goes up, direct relationship. Okay. When the temperature of the container increases, you're going to gain pressure because you're going to gain collisions. Okay. So same thing, kinetic energy, because you're changing temperature. You will, I apologize for it, does not like me writing in that chart. That kinetic energy will increase because you have more collisions. Anytime you're changing temperature, especially increasing temperature, you will have an increase in kinetic energy. So let's write that up here instead. So when you increase temperature, you will get more movement. And with that more movement can create more collisions. Okay? So when you increase that pressure, you will get more collisions. Not just with the walls, but also with the container. Let's see, with Gay-Lussac's, pressure goes up, temperature goes up, direct relationship. So it almost looks like Charles's law, except we just put the pressure in instead. So P1 T2 is P2 T1, okay? And what has to stay constant is volume in moles, okay? So Avogadro, same thing, direct relationship. If volume goes up, because you added more moles. So when this increase in moles, it means because you added more into that sample. So a balloon will increase in volume if you add more air into it, more moles. So you would have V1 in 2, V2 in 1. And what has to stay constant is pressure and temperature. Okay? So with the 3 gas laws, moles most of the time stayed constant until Avogadro. So the one we just learned right now, combined gas law, we put them all together. There's no graph, there's no picture, there's no example because it could be a mixture of all 4 of these as an example. So P1 V1 T2 N2 equals P2 V2 T1 N1. So a couple reminders. Pressure, volume, can be any units that you want, but they have to be the same unit so they'll cancel out. Same to cancel. Okay? Temperature, you don't have a choice. You got to use Kelvin. And moles, you don't have a choice because that's why it's called moles. Okay? Well, what if we wanted to say every gas was ideal? So if every gas was ideal, then there must be an equation I can use for every gas. Okay, so take a minute, read Learning Objective 3.4 and see the skills that AP says you should master. There is some unique equations coming in here. These equations right here, these last 3 lines, you'll see these more when we get to 10.6. So this part right here, I believe is coming in 10.6 when it has to do with partial pressure, okay? So take a minute, read, annotate, and highlight. The ideal gas equation is probably the #1 gas equation you actually see on the AP test, probably more than any gas equation. Hypothetically, if we say every gas behaves, and when we say behave, we're talking about chemically reacting, if they're all reacting like the same. So we call them ideally. Whether it's diatomic hydrogen, methane, argon, ideally, if they all have the same behavior, well then they should have the same calculation. So a way to identify this type of problem is you're actually going to see something. There's no more 1s and 2s. There's just a P, and then there's a V, and then a T. There is no P1 V1s or P2s or T2s. You have just one set of conditions. Okay? So only initial values and final values are for the 4 gas laws, or I apologize, 5 gas laws. So the 4 scientist gas laws plus the combined gas laws. You have to use certain units with this one. You have no choice, okay? With the other ones, pressure and volume can be any unit, but unfortunately with the ideal gas equation, you have to have ATM. With volume, you have to have liters. Moles is still moles, and temperature is still Kelvin. The reason why is this equation. PV equals nRT. This R has a name called the universal gas constant, which means if I say a gas is ideal, they all will have this constant. So this R, because I have pressure as ATM, I have volume as liters, I have N as moles, and I have T as K. That R value actually has 4 units, okay? And you have to write all 4 units. So liters times ATM, that little dot right there means multiply, okay? Doesn't mean a degree sign. moles times K. Same thing right there, that little sign, that means multiply. So the units of R force us to have pressure, volume, moles, and temperature in that specific unit. And I'll show you why when we get to the example below. What if you want to use, instead of ATM, maybe you want to use torr instead of ATM? Well, there is another R value you can use. It's just AP doesn't always put this one on your equation sheet. So I do know this one is on your equation sheet. So yay, something that we don't have to memorize. But you're going to have to look on your equation sheet to see if this one is. And if it's not, well then just stick to the torr. Or stick to the ATM. We know how to take torr and get to ATM. Let's practice our skills of algebra. If the ideal gas equation is PV equals nRT, what if I just want to solve for pressure? How do I get that volume to the other side? Well, I'm going to divide. So nRT over V. We're not memorizing 5 equations. We're learning one equation, which also on the equation sheet. Yay! But algebra skills, very important. Okay, that's why back in last year when I asked you guys, I got to see your math skills. I got to see what you can do in math. So that's what I need to see is algebra skills. What if I want to solve for volume now instead? Well, I'm going to take that pressure and I'm going to divide instead. So nRT over P. What if I want to solve for moles? Well, that means R and T have to get divided. So PV over RT. And if I want to solve for temperature instead, so that means moles and R get divided. So having solid algebra skills is just as important as having strong chemistry skills. Because if you can't rearrange an equation, you can't do the math and chemistry. And if you can't do the math and chemistry, then we got a problem of pretty much every chapter to come. So let's practice this. Assuming ideal behaviors. Okay, that's nice. Ideal gas law. How many moles of helium, so I'm looking for N, are in a sample that has a volume of 8.12, has a temperature of 0 degrees. Remember right here, this is not called absolute zero. Okay, absolute zero would be 0 Kelvin. And then I have a pressure of 1.2. So notice I don't have a P1, a V1, pressure, temperature, moles, all variables stay constant. So you're using the ideal gas equation. PV equals nRT. I want to solve for moles. So remember, if I'm going to solve for moles, I'm going to bring R and T over. But let's make sure we have the units that we need. Pressure needs to be in ATM. Volume needs to be in liters. Temperature does need to be in K. So Celsius plus 273.15. So 0 plus that. And I have 0.00, which means my temperature is going to be exactly 0.15 because of sig figs. So I got the temperature that I need. So moles is PV over RT. So let's write it out first. For helium, usually we would put it next to the value for mole, but because we don't, you could put it next to pressure or volume. I'm going to put it next to the volume, but it should be listed somewhere in there. Now the R, the gas constant, 0.08206 liters dot ATM over mole dot K. And you'll see why R has 4 units in just a second. Temperature is 273.15. Now, before you plug and chug, let's look at this. Liters, well, I have liters right there, so liters are gone. ATM, top and bottom, they're gone. Kelvin is on the bottom of the R. So cross multiply, that's gone. And what am I left with? Which is moles, which is what I'm trying to solve for. So when you plug this in the calculator, let me write it out. You guys plug it in. 1.20 times 8.12, and then hit that equal sign. Because you have two numbers in the bottom, you got to go divide R, hit that equal sign, and then divide 273, hit that equal sign. So let's all plug it in together. So 1.2 times 8.12, and then divide 0.08206, and then divide 273. And let's see if you get what I get. So question is, looks like we need 3 sig figs. So in the end, we should get 0.435. And we're going to say moles of helium. Okay? So not only make sure you copy down the work, but make sure you actually plugged it in to practice with your calculator. Okay? Let's try another one. Let's say I want molar mass. Okay? I have 2 liters, so I got my volume. I actually have 4 grams of gas. Well, that's mass. That's not moles. I have, and I don't even know who this gas is. I have temperature, but we know we got to get that guy. And because I already wrote my temperature equation up there, I don't have to keep writing it over and over. So I'm going to take that 18.0 Celsius, and I'm going to go 18 plus 273.15, and 1 after the decimal, 291.2. And I have my pressure. That's an ATM. So I have my volume in liters, my pressure in ATM, I got my T and K. And so let's calculate molar mass. Well, let's remember something about molar mass. In chapter 3, I taught you there's another way of writing molar mass. Grams or grams per mole. Why did they mention this 4 grams? It's because we need to get used to molar mass being grams per mole. So I got the grams, he's sitting right there, but I don't have the moles. So in this part right here, I got to solve for moles, PV over RT, and once I have moles, then I could take those 4 grams and divide by the moles. So be very careful that you remember chapter to chapter of things that I taught, because they're going to come back to you. We have our R, and then my temperature, 291.2. Okay, so let's plug this in. Looks like we're going to do 3 sig figs. So 1.08 times 2. And remember, now we're going to hit divide 0.08206, and then divide 291.2. So 3 sig figs, I'm looking at 0.0904. And let's check out our units. With our units, we have by ATM, by liters, by K, and look right there, there's my moles. So this is moles of this particular gas. So molar mass, okay, grams per mole, 4.00 grams over 0.0904 moles. So simply dividing 3 sig figs, and it looks like I'm going to get 44.2 grams per mole. They didn't ask us to identify who the gas was, so we're going to leave it like that. Okay? So don't forget chapter 3, grams or grams per mole. In the next video, you're going to see molar mass coming up again, because there's a way that we can use the ideal gas equation to solve for molar mass in a different way. Okay? But I'll give you a sneak peek on the next one. Let's try another example using the following unbalanced equation. Well, I see unbalanced, which means don't even read the rest. Let's get this balance. I see 1 aluminum on both sides. I see 1 hydrogen versus 2. I see 1 versus 3. I remember this equation from a previous example. I believe we had to do a common multiple between 3 and 2. So I'm going to put a 6 right here. I'm going to put a 2, and then I'm going to put a 3, and then a 2. So I believe I'm all balanced, but let's double check. 6 hydrogens, 6 chlorine, and 2 aluminum. Sweet. I have 35 grams of aluminum, so I like to write my info underneath. And that says excess HCl. Well, that just told me if he is excess, that means my aluminum was probably my limiting reagent. Not sure if we need it, but I'm just labeling what I know. According to the equation above, what's the volume of hydrogen? I want volume of him, but I want it in liters. Of this temperature and of that pressure. Well, my temperature is in Kelvin, my pressure is in ATM, so that's good. So not only am I using gas laws, the ideal gas equation, but I also got to do some stoich. So you have a choice. You could either, one, do the stoich first, go grams and go to H2, or, and I'll show you right there, so grams of aluminum, and because we're going to use the ideal gas equation, we want to go to moles. So grams of aluminum to moles of H2. And the reason why we want moles of H2 is because PV equals nRT. I need to put the moles so I can solve for volume. Can you use the ideal gas equation first and then do stoich? Absolutely. You could do either one, and I guarantee you're going to get the same answer. Okay? I always like to do stoich first and then do my gas law, but you guys can choose whichever way makes sense to you. So if I have 35 grams of aluminum, so now I got to get my molar mass of aluminum, which is 26.98 grams. And because the chemical is going to eventually change, we do got to write the chemical on each step. My equation says I have 2 aluminum for every 3 hydrogen. Now, I don't want to go to grams because ideal gas equation, that moles, that's moles. I don't want grams. So I'm going to stop right there. So let's plug in 35 times 3, divide 26.98, and then divide by 2. So it looks like 2 sig figs, 1.9 moles of hydrogen. So now I'm going to take my equation and solve for volume. So volume is nRT over P. So now instead on this step, I'm going to only divide by 1. So my moles, 1.9 moles, hydrogen. Remember, if you have moles, put the chemical next to the moles. My gas constant, liters.atm, moles.k. My temperature was 345, and my pressure 1.12 atm. So check out the units. My moles cancel because it's on the bottom. My atm cancels. My K cancels. And there's the liters that I need. So I'm going to use 1.9 times 0.08206 times 345 divide 1.12. And I'm going to get my volume. Looks like 2 sig figs, so 48 liters of hydrogen. And there it is. So it's a little bit of chapter 3 with a little bit of chapter 9 or chapter 10. All right, had a brain fart there. All right, a little bit of chapter 3 with some chapter 10. Let's practice a little bit of stoich, but what if you're at a certain condition? Okay, so we can use stoich for any set of conditions using the ideal gas equation, but only under one set of conditions. Okay, there is a way instead of using the ideal gas equation where you can bypass the ideal gas equation and just use stoich. but it can only happen in one instance. Notice the example that we did above. I had to use stoic, and then I had to use the ideal gas equation. Well, what is this one condition? So let's assume you have 1 mole of an ideal gas at 0 Celsius at 1 atm. Then what would be the volume? Well, the volume is called something molar volume because the word molar has to do with moles. So there is a cool trick that if, this is the very important part, if your temperature is at 0 degrees, 273 K, and you're at 1 atm, we call this something important called STP, standard temperature and pressure. And if you have that, that means 1 mole of any gas at that temperature and pressure will always have a volume of 22.4. This is going to save you a lot of work. And if you don't see it at first, it's okay. That just means you're doing double the work, but you're still going to get the right answer. So 1 mole equals 22.4 liters at STP. And this has a name called molar volume. You can use this for any gas, but only at STP. Not solids, not liquids, not any other temperature or pressure. Okay? So at 0 degrees Celsius, 1 atm, let me show you how to work this. Okay? So it's either one of two ways. You use the ideal gas equation with stoic for any set temperature and pressure versus STP, then I only have to use stoic. Okay? So let me show you where. Remember on the stoichiometry chart, we had done every box around here, but we never did volume A and volume B. Well, now here it is. See this thing called molar volume? That's 1 mole, 22.4 liters. Hey, look at it. It's right there too. Okay? So, volume A, well, I can get to moles, same chemical. Then I can use my balanced equation to change to a different chemical, and then go back and use 1 mole, 22.4 liters. Okay? So let me show you that. How many liters of oxygen at STP? Ding, ding, ding. That means I'm going to just use stoic. And I'm not going to use a gas law. So not going to use a gas law. I want to know liters of oxygen that are required to react with ethane. With that much liters of ethane. And I told you the formula of ethane, C2H6 at STP. Well, people, we need a balanced equation. So ethane gas reacts with diatomic oxygen. And what type of equation is this looking at? Well, this is combustion. So I'm going to get my CO2 gas, and I'm going to get my water. Okay? So quick balancing, I'm going to put a 2 on my carbon. I have 6 hydrogens. I'm going to put a 3. And if I count up my oxygens, I have 4 right here plus 3. So it looks like I have 7 halves. Okay? When I do math, I don't like to use my diatomic fraction. So instead, your coefficients without that fraction, you would just multiply everything by 2. So 2, 7, 4, and then 6. That is the other option you could do. So let me show you where I'm at. Right here, I'm at O2, or I'm sorry, I'm starting at that ethane. I'm going to go to moles of ethane. I'm going to come over here to oxygen, and then go to volume of oxygen. All right, 3 steps. So I'm starting with 7.98 liters of ethane. Now, because I said STP, molar volume, STP, then 22.4 liters, 1 mole on top. I still got to put the chemical everywhere because eventually, this step, I'm going to get rid of the chemical. So 1 mole of C2H6. And then on top, I want, what do I want? Oxygen. So I'm going to put 7 here. All right, back to my equation. Apologies, I had to pause right there. I have my 7 moles of O2, but if I'm going to use these whole numbers, I'm going to put a 2 down here at the bottom. Okay. Originally, I had a 1 because if you do decide to use the red numbers, nothing wrong with it. You put a 1 down here and then a 7/2. If you notice, ladies and gentlemen, you're going to multiply by 7, divide by 2. Same thing right here. Multiply by 7, divide by 2. So let's plug this in. So bye-bye C2H3. I'm going to get my oxygen. And 7.98 times 7. And then divide 22.4, divide by 2. So looks like, what are we looking at? 3 sig figs. And I'm going to get 1.25. And I want, or I apologize. I need to go one more step. I want liters. I was stopping at moles. I want liters of oxygen. So right here, I have moles of O2. And I'm going to go right here to volume. Well, I just need molar volume. It's basically this step again, just with a different chemical. So 1 mole of O2 and then 22.4 liters of O2 on top. So bye-bye moles. But notice right here, look, 22.4, 22.4. So I don't have to plug that 22.4 in the calculator because it's on top and bottom. It'll cancel. So what am I plugging in? Let's highlight. I'm going to plug in that 7.98 times 7, divide by 2. And this is why you can do stoichiometry with ideal gases. As long as you're at STP, you don't have to use the ideal gas equation. So 3 sig figs, because I'm basing my sig figs off that starting number. We never look at the moles. 27.9 liters of O2. And there it is. Let's do some more so you see the difference. Okay. 42 liters of ammonia. How many moles of nitrogen can be used, assuming under standard conditions? And they just told you right there, standard conditions, STP. Well, how many liters of ammonia, a process requires ammonia, how many moles of nitrogen are needed to react? Well, this is an equation that's producing ammonia, starting with nitrogen and hydrogen. This is a very famous equation in chemistry. This is basically how fertilizer was invented, ammonia. Okay, ammonia is like one of the biggest components in fertilizer. It's called the Haber process. And you're going to see it pop up in chapter 14 where we're going to talk about it in the beginning. Okay, real quick balancing. It looks like I'm going to need a 2 on nitrogen and then a 3 on my hydrogen. So if I have 42 liters that I want to produce of ammonia, how many moles of nitrogen would be required? Okay, so same thing. I'm going to go 42 liters. And because I'm at STP, I can use my molar volume. 1 mole on top. And now let's get rid of ammonia. For every 2 moles of ammonia, I have 1 mole of nitrogen. Well, I'm going to stop right there because I want moles. So I got rid of ammonia. So basically, I'm going to take 42, divide 22, divide by 2. So make sure you guys are plugging this in the calculator. You never know, Rodriguez could make a little boo-boo. 2 sig figs, 0.94 moles. There you go. Good job. Last one, because I want you guys to try one yourself. What if I had molecules? I have molecules of hydrogen. Well, you know we can't use molecules. Okay, so I got hydrogen. And it says I have excess chlorine. How many liters of hydrogen chloride gas can be formed at STP? So that just told me I can use stoichiometry. So first, we need a balanced equation. So I'm going to start the skeleton for you. And then hydrogen is +1. Chlorine's -1. So HCl as a gas, though. Okay, not an acid. So make sure you balance that. Okay. I want to get to, it looks like, liters of HCl when I'm starting with 5.33 times 10 to the 23rd molecules. Now the reason why it's molecules is because H2 is nonmetals. It said chlorine was excess. So if I was doing a limiting versus excess, that means hydrogen would be my limiting. Okay. So number 1, balance your equation. So 1, balance the equation. Okay. 2, because I'm at STP, we're going to use some stoich. But how are you going to use the stoich? You got to take these molecules and get to moles. And what do you need to get from molecules to moles? I believe you should use some Avogadro. We're going to change those moles into HCl. And then we're going to use, so right here we need our balanced equation. And then for moles to liters, we're going to use our molar volume. All right, and if you do this right, and I didn't put the answers up here, but I will before I print, looks like we should get about 1.77 liters of HCl. Okay? See you on the next one, AP.